All right, everybody, hello and welcome back. Today what we're going to do is we're going to work on discussing exponentials and logarithms, or logs. So if you take a look at our warm-up problem here, it says 3 to the third power is equal to, well, 3 times 3 is 9, times 3 is 27. All right, so this should be something we're comfortable with. We've done it before. We've talked about exponentials. We now have 5 to the third power. That's saying 5 times 5 times 5, which is 125. And then we have 4 to the negative second. Now, negative exponents are not something we typically deal with. However, in order to get rid of our exponent that is negative, we need to remember that 4 is really 4 over 1. So to get rid of our negative, we move the value with the negative exponent to the denominator, or vice versa if it already is in the denominator. So this would become 1 over 4 squared, or 1 over 16. Now, similarly, we've got a new type of problem here that's going to look a little bit different, but the idea should be the same. It says 2 to the blank power is equal to 8. So this time, instead of knowing the exponent, knowing the base, and finding the answer, we now know the base, and we know the answer. We need to find the exponent. So 2 to the third power is 8. Now it says 12 to the blank power is 1. Well, anything to the 0 power is 1. And then we have 4 to the blank power is 64, and that is going to be the third power. So these types of problems are pretty similar that we have on top and on bottom. However, it really is different thinking, all right? In one, again, we know the base, we know the exponent, we're finding the answer, and that's usually what we're most comfortable with, these problems up at the top here. We're usually pretty comfortable with these ones. Now, these ones on the bottom are a little bit different. The thinking is different. However, it's really the same process, except in this case, we know our answer and we don't know the exponent. We're kind of doing the opposite or the inverse of what we're doing in our problems above. This is what is called a logarithmic function. It is the inverse of an exponential. And now what that means is we are doing the opposite. So I'm going to show you the notation, and we'll take a look at a few examples. We have log base b of a equals x. So it sounds very strange to us, right? We've never heard anything like it. So let's take a look. Our b is our base, and this is like the same base we would have if we were talking about an exponential. A is our argument. And then x is our exponent, or answer. So we would say log base b of a equals x. Now, what logs really mean is 3, in this case, is our base. Maybe I'll set it up like this. 3 to what power is equal to 27. So it's just like that second round of problems we did in our warm-up. It's just like an exponential, but again, instead, we're solving for the exponent. We know the base, we know the answer, which is our argument, and we're looking for an exponent. So it's 3 to what power is 27? Our answer here is 3, as we discussed before. Similarly, we have log base 3 of 1 over 9. So remember what that means is 3 to what power is equal to 1 over 9. Now, most of us might realize that 3 to the second power is 9, but we need that to be in the denominator, so the exponent needs to be negative. It is a negative 2. So again, it sounds really strange. Logs look very confusing, but they're really not that different than anything we've done before. Instead, it's an exponential where we have different pieces. It is the opposite. We have the base, and we have the answer. We don't have the exponent. Now, we've got a couple unique cases down here. If you take a look, this one looks just like the problems we were previously working on, except there is no base written here. Now, this is what we call the common log. And essentially, it is the exact same thing, except there's no base written, but that base is actually 10. So whenever you see log with no base, we just need to know that the base is 10. And you might see this button on your calculator. So we need to think about 10 to what power is equal to 100. Well, hopefully that should be pretty easy. The answer for us is 2, because 10 to the second power is 100. All right, so this is the common log. But then we've got a problem like this. So first of all, E throws us off a little bit, but if we remember from our last unit, E is really just 2.718 approximately. 2.72. It is an irrational number, kind of like pi. Essentially, it's a symbol that represents one value. Again, it's not a variable. It's not something that changes every time. Now, we've got something that looks like an ln, and what this is our natural log. And the reason it is a natural log is because the base that is not written down here is e, or the natural number e. So since it is the natural number e, we have the natural log. So what this is saying is e to what power is equal to our argument, which is e to the second. So therefore, the only way that these two things can be equal is if the exponent over here is also 2, which means our answer would be 2. So let's summarize real quick. Logs are basically, they are, in fact, the inverse of exponentials. They're the opposites. We're just looking for different pieces. Instead of knowing the base and then the exponent and finding the answer, we know the base and the answer, and we are finding the exponent. You're just solving for a different piece of a similar equation. Now, again, we've got the base, which is the subscript, the number that's a little bit lower. A is our argument, and x is going to be our exponent that we're looking for, or the answer. We would say this is log base b of a equals x. More specifically, log base 3 of 27, which is saying 3 to what power is 27, and the answer is 3. We've got a couple unique cases. We have the common log, which is when there is no base written here, and when that's the case, the base is just 10. And then we have our natural log, which says ln, which is called the natural log because the base is our natural number e. So essentially, it works the exact same way. However, the base that is not written in this case is e. All right, so what we just did to go from, I guess I could rewrite this one as well. Here to here is we're going from log form to exponential form. We are going from log form to exponential form. And in the beginning here, when we're first solving logs, it's going to be easiest to solve logs or evaluate logs by switching forms. But we could also do problems the other way around, where we have something like this. 5 to the second power is equal to 25. Well, this is an exponential. So if we switch from exponential to log form, well, the base of my exponential is 5, so that means the base of my log is also going to be 5. My argument is like my answer, that's 25, and we are solving for the exponent, which is 2. Let's do... Why don't we do a variable here just to shake things up a little bit. So we have the exponential. 4 to the second power is equal to x. What that means is log with a base, well, the same base as my exponent, which is 4. My argument is going to be x because logs solve for exponents. So log base 4 of x should be equal to my exponent, which is 2. So here we're going from our exponential form to our log form. And it would work the same way if we had something like 10 log base. Well, the base of my exponential is 10. So I would put a 10 down here, but remember that's a common log, so we don't need to write it. And then we put our 1,000 as our argument, and logs solve for exponents. So my exponent needs to go here. Finally, we could do the same thing with e. We have e to the fourth power is equal to, again, let's throw in another variable. Why don't we do this? Let's switch it up. So e to the x power is equal to 4. Well, we need a log, but that log needs to have a base of e. So that's going to be our natural log. Our argument is our answer, and logs solve for exponents. So the exponent is going to be x. So these two things are exponential form and log form. So you need to be pretty comfortable switching between the two and evaluating. If you want to, you can do this on a calculator as well. For natural log, you could just type in our value for the natural log. I just typed in ln. If we want to do a common log, again, you could just type log. Like this. Or we could even click functions and scroll down until we see log with a base of a. So I could put in values here. There's my base, there's my argument. Log base 2 of 8 is saying 2 to what power is 8, and my answer is 3. All right, and we could also do not so easy numbers. 2 to what power is 10? Well, most of us should recognize that that's not going to be a simplified, nice answer because 2 to the third power is 8 and 2 to the fourth power is 16. So our answer is going to be not so pretty here, but again, we can evaluate with our calculator by simply plugging in. Okay? As always, thank you for listening. If you have any questions or concerns, please feel free to reach out.